Hello everyone, welcome back to another lecture on data structures. In this case, we are discussing Floyd's algorithm. So last lecture, I discussed about Dijkstra's algorithm, which ultimately gave us the cost of the shortest path going from a specific source vertex to any other vertex. The all-pair shortest path problem is a bit different and it's a bit better in the sense that rather than choosing just or getting the cost from one vertex going to all the other vertices, APSP will be able to give us the result coming from any specific vertex to another vertex. What does that mean? The result of Dijkstra's algorithm only gave us the cost of the shortest path from 0 to 1, 0 to 2, 0 to 3, 0 to 4. What if I wanted to know the cost of the shortest path from 3 to 1? I wouldn't know, diba? I wouldn't know. So I would have to call Dijkstra's again for vertex 3, so I would know the cost of the shortest path from 3 to 0, 3 to 1, 3 to 2, and 3 to 4. And if I wanted to know about the cost of the shortest path from 4 to anything else, I would have to call Dijkstra's again to be able to build that this D, which is the cost of the shortest path, or an array containing the cost of the shortest path. APSP is basically the problem that I am discussing right now, or that I was discussing, which is how would I know the cost from any vertex to any vertex? So from a source to a destination. From Dijkstra's, we only have a specific vertex going to everything. But then we wouldn't know from another vertex to another vertex other than by calling Dijkstra's again. So by the end of APSP, which will be solved with using Floyd's algorithm, we would be able to answer any cost of the shortest path for any vertex. So in the APSP problem is to find any for each ordered pair of vertices, we want to be able to find the cost of any path from V to W. This problem can be solved using Dijkstra's algorithm, but in this case, we call it an n number of times for the n number of vertices. So if we call Dijkstra's algorithm for 0, 1, 2, 3, and 4, meaning we call it 5 times for each vertex, we would be able to get 5 different results, or 5 different Ds, such that D is an array containing the cost, or the shortest cost, smallest cost, going from a vertex to all of its other vertices. So the result of doing this specific step would give us 5 arrays of 5, which means if we were to merge them all together, it would become a multi-dimensional array. And that is essentially what APSP, or the solution to APSP, is. We would have a multi-dimensional array containing the smallest cost for the shortest path going from a vertex to another vertex. And this is solved using the Floyd's algorithm. So this algorithm computes the shortest path from any given vertex to any other vertex given the arc cost matrix C. We will be able to see what an arc cost matrix looks like. It's basically something like this, or basically our adjacency matrix. So given an adjacency matrix, we will be able to compute the shortest path from any given matrix to any other vertex. The result will be stored in an n by n matrix A. So this, my friends, or my beloved students, is Floyd's algorithm. And it's very color-coded by Ma'am Peña. Thank you so much, Ma'am Peña. Shout out to you. Bless your soul. Oh my god, I shouldn't say bless her soul. She's alive, you know, but bless her. Peña is amazing. So anyways, you will notice that Floyd's algorithm has 3 different steps. we have this specific for loop, this specific for loop, and this specific for loop. And honestly, I don't want to, not really don't want, but I don't think I should even be simulating this anymore, because this is something you guys can do very easily. Because it's just 3 for loops, if you had the patience to draw this, it would be very easy to visualize. But anyways, I'll just give you a gist of what is going on. The first for loop, or the first step, is basically, you will notice we are doing I equals 0, I less than n, j equals 0, j less than n. I'm not sure if you remember this, but that's basically a complete traversal of a 2x2, not a 2x2, a complete traversal of a multi-dimensional array, or a 2D array, going from index 0 to index 0 of I and j. We're basically traversing the entire 2D array. And while traversing the entire 2D array, I'm copying what is in C going to A. So this entire for loop just copies whatever is in C, copy it into A. Okay? So if we look at this, this is my C. The first for loop copies everything that's here, and it will copy it here. Okay? So it's just copying C to A. Sir, that looks very inefficient. Not really. I don't know if somebody will say that, but I'm sure one of you guys would say, sir, I'm copying an array into an array. Can I do memcopy? Yes, you can. So you can also just replace this specific step with memcopy. Essentially, you're memcopying into A, coming from C, and then you do your memcopy. Okay? Next, for I equals 0, I less than n, A at index I. What does index I mean? That's basically the diagonals. When I is 0, it's referring to 0, 0. When I is 1, it's referring to 1, 1. When I is 2, it's 2, 2. And if we were to look at that, that's 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. So what is this doing? It's setting the diagonals to 0. So you'll see all my diagonals are 0. Why is that? It's because the cost of the path from a vertex to itself is 0. Very good. Let's go on to the green. So for the green, we are doing a 3 sets of for loops. But the essential thing we need to know about these 3 sets of for loops is we are doing something similar to Dijkstra's algorithm. So if you remember in my previous lecture, I said something about min, the min function. You don't actually have to have a min function. You can just do, if this is less than this, then I'm going to use this. Otherwise, I'm going to use this. That's the same thing I'm doing here. If the left side, or in this case, gibali nila, but basically, if the current shortest path is bigger, or if the new shortest path is bigger than the old shortest path, then I'm going to update it to be that value. Otherwise, I don't change anything. So that's Floyd's algorithm. You know, for things like this, especially when the pseudocode is already like this, I would just say trust the process. I assure you that if you were to code this, this would work. Like, out of the box, this would work. So, this isn't even a simulation at this point. I just want to show you that this would be the resulting matrix. And to prove that it is just similar to Dijkstra's algorithm but on steroids, we can prove that using row A. Row A contains the cost of the shortest paths from 0 to 0, 0 to 1, 0 to 2, 0 to 3, 0 to 4. 10, 50, 30, 60. If we look at the result from Dijkstra's, it's 10, 50, 30, 60. So it just means that if you wanted to do this using Dijkstra's algorithm called an n number of times, you can just store the result sequentially in each index. So if I were to call Dijkstra's for vertex 1, this would be the result. But it's just the same if you use Floyd's algorithm. So what did we learn today? We learned that Floyd's algorithm allows us to get the APSP matrix, which is a matrix that contains the cost of the shortest path going from any vertex, any source vertex, to any destination vertex. And if you want to code it, this is how you code it. I would even argue if you copy paste this will work. So it's important for you guys to be able to know the steps and to be able to code this, but then this amazing pseudocode already contains everything. Kuwang na lang siguro, if you want, you could have something that would return this one. If you want, you could return this one, and that's not being included in the pseudocode. But yeah, Floyd's algorithm, very easy. You don't need to be concerned about Floyd's. Just trust the process and code this. But if you have any questions, you're free to ask. Thank you, everyone. I hope you were able to understand Floyd's algorithm, which essentially gives you a matrix that contains the cost of the shortest path from any specific vertex to a destination vertex. If we want to mata-mata, let's just try. The shortest path from 2 to 4 is 10. 2 to 4 is 10. Try something else. The shortest path from 3 to, let's say, 4 is 30. 3 to 4 is 60, so this isn't actually the shortest path. 3 to 2 to 4 is 30. 20, 10, 30. And that would work for any specific set of vertices. Okay, we're good. Thank you, guys. Hope you are preparing for the exam. See you all in our next lecture.